Hi there, I'm Charlie and welcome to my 6.3 presentation on the numerical model. So what is the numerical model? This is a set of collected numerical data that can help you work towards an ideal performance level that you might want to achieve, such as getting faster or in this case becoming better at rebounds. It consists of several different fundamental components, and these are, as you can see on the screen, vectors and scalars, distance and displacement, speed and velocity, acceleration, and Newton's three laws, and I'm going to explain those now. So, first of all, vectors and scalar quantities. The vector quantities, these have a magnitude and a direction. So, for example, in basketball, how fast the rebounder jumps and lands. So it adds all that together. The scalar quantities is these only have a magnitude for how big and fast something is. So this translates to rebound in basketball, where the size or speed of the rebounder can increase or lower their chances of getting the rebound. So it might mean they can jump higher or lower, or they can move a bit more agile or not move as agile. Distance and displacement. Distance is the sum of every movement that's taken place. So this means that if, say, a rebounder has travelled 10 metres forward and 5 metres sideways, left or right, in order to get into a position for a rebound, their overall distance is going to be 15 metres, because that's the sum of every movement they've done added together. Displacement is slightly different in that it's the distance from one point to another, not including the direction, so that's just from point A to point B, not moving around left or right. It doesn't account for that, that's regardless. It can be used in a basketball game when getting rebound, in that if the rebounder is on one side of the court and needs to get to the point on the opposite side of the court where the rebound is going to take place, and this distance between these 2 points is, say, 13 metres away from the position where the rebound needs to take place, the displacement from the point they're currently in to that point where the rebound needs to happen is going to be 13 metres away, and that's going to stay the same regardless of how far they move left or right on the way there, like maybe weaving in and out of other players or avoiding screens, pick and roll defense or offense. So yeah, the overall displacement of that movement would be 13, because that is simply how far it is from that point to the other. So speed and velocity. Speed is measured in meters per second, and this is how quickly the body moves. It's calculated using the equation speed equals distance divided by time or over time. Calculating the speed will be useful in a basketball game because it can be used to calculate how quickly the rebounder is able to get to the spot in order to make a rebound. Once the speed is calculated, it can be used to perhaps improve the positioning of the rebounder in case they were not quick enough before. So maybe they weren't quick enough and someone else is already boxing them out and stopping them getting the rebound, where perhaps if they're a bit quicker or in a better position where they didn't have to use their speed as much, they would be able to get there first and would have a higher chance of getting it. The velocity, this is also how quick the body moves, but it's in a specific direction. So what this means is it's also measured in meters per second, and it's calculated using the equation velocity equals displacement divided by time, because it's about direction. This is useful in a basketball rebound because it can be used to work out what the player's velocity is when they're running up to catch the rebound. So what this means is it can be used to decide maybe if they were going in with too much speed before, and that maybe lowered their chance of having the rebound. And if they perhaps went in with a lower velocity and a bit more calm and collected, they wouldn't maybe foul someone else, or they'd be more controlled with a lower sense of gravity, lower centre of gravity, so they are balanced when they're about to take the rebound and they're not unbalanced because of the velocity they're travelling at. Acceleration, this is the speed of change of velocity for speed. It is also measured in meters per second. Acceleration is calculated using the equation change in velocity or speed divided by time. Acceleration is important to know in a rebound because it could help knowing how much acceleration is needed in order to be able to get to the spot where the rebound will take place in time. So perhaps after a game and you're looking at the recording of the game, you might see that if you had a better acceleration or you were closer enough, if you were closer, then having acceleration may help you get to that spot quicker than, because maybe if your acceleration wasn't good enough, there might have already been someone from the other team there already and could get the rebound over you. But maybe in the next game you would think, from the game tape that I've seen, if I use my acceleration in a certain spot, perhaps a bit closer to the rim, then you have more chance of getting the rebound. So Newton has 3 laws. First law is the law of inertia, and what this is that everyone or everything is moving at a constant motion and speed unless countered by a change in force. So what this means, this translates to a basketball rebound in that as the rebounder is on its way up, if there was no other forces acting upon him or her, they would just keep going until something stopped them. But what stops them is the gravitational pull of Earth. So that's why they come back down, because there's a force acting upon them. The second law is the law of acceleration, and this is the acceleration of a body is proportional to the force actually creating the acceleration. So the acceleration takes place in the way the force acts. This translates to basketball rebound, where the more force applied to the floor by the feet of the basketball player or the rebounder, the more upper thrust they're going to be able to get when they jump up, and the higher they're going to be able to get, which will obviously increase their chance of the rebound because they'll be closer to the ball over their opponents. And the final one is the action-reaction. What this is it states that wherever there is an action, there is always an equal and opposite reaction against it. So action meaning forces, so there's always an opposite force acting upon that force. So in the basketball rebound, when the rebound is being performed, the force of the player moving up is countered and matched by the force of the gravity bringing them back down, which then causes them to obviously come back down. Otherwise they would just keep going. So now moving on to the methodology of the numerical model, so how it actually is gathered, how the information is gathered. Participant preparation, and so this starts with a PAR-Q test. What this is it's finding out about any contraindications that could possibly stop the participant partaking in that activity. So if you're pregnant or have had a heart disease where you were told by a doctor that you shouldn't be exercising because it could affect you or cause fatal damage. So that's what a PAR-Q is for. It's finding out about any things that could stop you taking part in that activity. It's taken in the form of a yes or no sheet. A warm-up also takes place to help the players' muscles warm up for that exercise. In our case it was a standing vertical jump, so what we did was we did about 2 minutes on the spinner bike with a bit of resistance on the wheel, so it was harder to push, which then got our pulse raising and the blood pumping to our muscles, which then when it comes to doing the actual jump, your body's more ready, and your body knows you're about to do some exercise, so it could vary if you didn't do the warm-up. And the final part is explaining the rules and protocols of that activity. So for us, the rules and protocols were that when doing the vertical jump, we were not able to bend our legs any further than the angle that we were jumping from, and those angles were 45 degrees and a 90-degree angle. We did 2 separate jumps. Another rule was that we had to measure our weight in newtons in order for the force plates to measure how far we were actually jumping. So what this clarification of protocols means is that when we stand on the pressure plates, it then takes our weight, and once it has our weight, it can then tell us, using our weight, the force produced when we actually have that boost of jumping up off of it. And then from that it can tell us obviously the force produced, and then it can also tell us our height by measuring our weight 100 times a second. Another thing is the equipment preparation of the methodology. The camera is a big part because there are lots of components to the camera that can affect perhaps the data that you gather, because for example the shutter speed, this is where if your camera has a high shutter speed, that means it's going to be able to take images that are a lot more clear. As you can see in the image, this one is at a low shutter speed, so it's quite blurred. You can see the water's blurred. However, this one down here is a high shutter speed, so you can see there's a lot more detail and you can get a lot more precise readings of, in our case, how high we jumped, or if we bent our legs during an angle. Another factor with the camera is the frame rate. So in this photo, if you have a low frame rate, this photo is on a 30 FPS, which means frames per second. Basically, the higher the frame rate is, the more smooth your camera is going to be able to capture that footage and make it easier to look at. So again, it can help you get a lot more accurate readings depending on the frame rate. Also, the aperture, or the iris of the camera, and this is actually how wide the shot is. So if you're in a small room perhaps, you would want a large aperture, so when the camera's on them, as soon as they jump, they're not going out of the camera because it's a large kind of view. They're not jumping out of the shot where you can no longer see the readings. They're in the shot the whole time, so you can see the whole time what they're doing. If they perhaps did something wrong or did something that was against the protocols, you can judge that a lot more easily. Another thing is the pressure plate setup, and this I explained before was the standing on the pressure plate, gathering our weight in newtons, so it can then go on to predict tell us what our force produced was. The video was also set up on the iPad in our situation where this used all of these things, so frame rate, the shutter speed and the aperture of the camera. So it was made sure that it was a good distance back, so it was able to see us the whole way during the jump, so we never went out of the shot. So this is actually the numerical data that we gathered when we were there between myself and Aaron. This is Aaron's. He jumped 0.37 meters, and here is his. These are different stages. The braking phase is just before you're about to jump, and the propulsion phase is as you jump. So yeah, that is Aaron's data. Moving on to Charlie's, mine. Jumped 0.44 meters, and the impulse was 188, and Aaron's impulse was 174. Okay, thank you very much for watching.